evening, everyone, and thanks very much for coming to IMET for this public lecture this evening by Trevor Needham and Kevin Sowers on PCBs. For those of you who I haven't met, my name is Russell Hill. I serve as the director of IMET, and I want to just spend a minute or two telling you about IMET before I introduce our two speakers in a little bit more detail. So, we've been around a long time. We've been in this building since the end of 1995. We are a leading research institute with really a unique structure. We are a partnership between 3 different universities in the university system in Maryland. UMB, the University of Maryland, Baltimore, and some of our faculty are affiliated with the School of Medicine, the UMBC, and our third partner is UMBC, the University of Maryland Center for Environmental Science. So we are an example of how the different universities can collaborate well to achieve excellence, and we aim to be the best marine and environmental research institute in the world. We're making good progress towards that. So we have a lot of exciting work happening here. We're working in the areas of food and energy and human health, and as you will hear today, environmental sustainability. And the research you'll hear about is a great example of how we can clean up some of the environmental problems that we have. So a couple of other quick points. We train graduate students. We have around 25 graduate students, mainly doing their doctorates here at IMET, and we provide them with extra training through some generous support from the Radcliffe Foundation. We provide them with training on entrepreneurship and leadership. So this sets them up to be able to start their own businesses if that's the career path they decide to go down. So just remember the range of science, the fact that we are doing training of graduate students, and we have world-leading research programs and things like sustainable aquaculture, and you'll hear more about that in our next public lecture by Yoni Zohar. There'll be an announcement about that soon. Energy and the other areas that I mentioned. So moving into the lecture this evening, I'm very happy to be introducing our two speakers. So we're going to start off with Trevor Needham, and Trevor is a graduate student at the University of Maryland, Baltimore County. He's in the Department of Chemical, Biochemical, and Environmental Engineering, where he's working in the group of Professor Upal Ghosh, and Upal's a long-standing collaborator, Kevin Sowers. So some of Trevor's work featured recently in the Baltimore Sun and in the Washington Post. Trevor also received the Best Student Presentation Award at a regional meeting recently of the Society of Environmental Toxicology and Chemistry before he moved to UMBC for his graduate studies. He did his undergraduate work at the University of Scranton in Pennsylvania. So Trevor, it's great to have you here joining with Kevin to give this lecture. Kevin did his PhD in anaerobic microbiology at Virginia Tech in Blacksburg. And Virginia Tech historically is one of the very top groups in the world working on microbes that grow without oxygen, on anaerobic microbes. So Kevin finished his PhD there in 1984. He then did a postdoctoral research and was a research associate at UCLA. He's been at IMET since 1991. He has been a full professor since 2006, and he also serves as IMET's Associate Director. And some of the work that you're going to hear about, you'll hear Trevor's recent contributions to this program, but this work I always hold up as a great example of what we do so well at IMET, because the work you're going to hear about from Kevin started off more than 20 years ago, when he took a sediment sample from Baltimore's Inner Harbor and he started isolating these microbes that can degrade PCBs. And he's made many research contributions in his time at IMET, but just in the PCB area, he's published more than 35 research papers. So there's a big foundation of work underlying what you're going to hear about today, and it's now at the very exciting point where all that fundamental research is paying off in terms of practical applications. So a really exciting story, and I'd like to hand over to Trevor to start off. Thank you.
All right, well, thank you so much for inviting me here to speak, and thank you, Kevin, for inviting me to speak. I've been working in Kevin's lab for a large portion of my PhD. The joke is that he's turning me into a microbiologist, which I'm actually an engineer by trade. And Kevin asked me just to give some context to the talk, sort of the so what of why should we care about PCBs. So the title that we came up with was From Miracle Chemical to Environmental Hazard, the Legacy of PCBs, Problem in the Baltimore Region, and Possible Solutions. So I'm going to start off telling you about the problem. So I'm going to be the bad news, and Kevin's going to be the good news tonight. So for those that may not be familiar with it, PCBs are polychlorinated biphenyls. They're originally manufactured as a flame retardant in 1929. And you can see this electrical transformer, which is a pretty common sight on most of our poles. There was a period of time where it was actually mandated that all of these be filled with PCB oil. Before PCBs were invented, or manufactured, I should say, these had a tendency to overheat, catch fire, and explode. And they did that pretty regularly. So they needed to have an oil that was very stable, didn't conduct electricity, and didn't catch on fire. So what they did is they took a biphenyl ring, which you see the basic chemical structure up there, and they stuck a whole bunch of chlorines on it. And every time you add chlorines to a molecule, it tends to get more persistent and more stable. And it ended up with this mixture called Aerochlor, and there's 209 possible PCB mixtures. Unfortunately, the chemical engineers did a really good job. And these things stick around forever. So they accumulate in the environment, they don't break down, they're highly stable, they don't catch on fire. And it turns out they accumulate in fish, and they are a human carcinogen, a neurotoxin, an endocrine disruptor, and they cause liver toxicity. So it tends to be a pretty big problem, and it's pretty ubiquitous in the environment. One of the big cases that most people hear about is the Hudson River. So General Electric had a PCB transformer maintenance facility where they estimate they dumped 1.3 million pounds of PCBs into the Hudson River, resulting in 197 miles of contaminated watershed. So far, GE has been working very hard to clean this up. They've spent an estimated $1.2 billion for cleaning up 20 miles of the river. A conservative estimate from what I've seen, I think 1.2 is what they report to their shareholders. Most estimated between 2.2 and 2.4 billion dollars. But to their credit, GE was some of the first people to start a lot of the research that we're going to talk about here tonight and have funded most of the PCB cleanup research that's happened. But yeah, so a real big problem and has a big price tag associated with it. So as I mentioned before, what are the chemical properties? So the same things that make them super useful also make them really persistent and a big problem for us. So the biggest one is they're persistent, they bioaccumulate, and they're toxic. They're really hydrophobic, so they really don't like water, and they love fat. So they end up a lot of times in the fat tissues of animals. They're chemically inert, and they're non-flammable. And one of the other issues with them is that they undergo some really interesting fate and transport phenomena. So they like to stick to sediments, they don't like to be up in water, but they also undergo what's called long-range atmospheric transport. Basically, they evaporate up into the clouds, move further away, and then it's rained back down. And it continues to do this, and they find they'll actually deposit around the Arctic Ring. And some of you may have heard about PCBs in the news recently because they're predicting a collapse in the killer whale population globally due to PCB concentrations in their tissue. So these biomagnify, so the higher in the food chain you go, the higher the concentration you have. And because killer whales are the top of their food chain, they tend to be the highest concentrations. But a really interesting paper I love just to show people, you can actually see where PCBs were used if you take samples of butter from around the world. And because they go up into the clouds and rain down onto grass, which is grazed on by cows, they will accumulate in the fat in cow's milk. So you can sample butter from alpine cows and alpine fields, and you will find PCBs in that butter. So I hope I didn't ruin breakfast for anyone, but just kind of a little perspective, it's really interesting to think about. So PCBs are classified as a legacy contaminant. They were banned in 1979 with a lot of other toxic compounds like DDT, chlordanes. Question is, are legacy contaminants still relevant? If we look at the Chesapeake Bay watershed, these are our fish consumption advisories. Most of the Chesapeake Bay watershed has a fish consumption advisory associated with PCBs. So you are not unlimited to consume fish based on the risk to human health. And I'm going to go into this a little bit about what does this risk really look like, but you'll tend to see different limits like do not eat versus 1 meal per month, 2 meals per month, 4 meals per month, 8 meals per month, or unlimited. And this is based on the concentrations in the tissue. So one of the things that our lab does at UMBC is we do this monitoring for Maryland Department of the Environment. So they send us fish samples every year. We monitor what the levels are. This becomes the advisories. So if we look at by basin, kind of divide up some of these different basins looking at it, the letter codes are up on the far right. Essentially, we have the red is our rural areas, so the areas like the Eastern Shore. The yellow is the more urban areas, and the gray is our more suburban areas. And this is for white perch, which is a very common fish that you'll probably see people actually catching out behind IMET and is consumed pretty regularly. This is a fish we like to look at because it's got a really small home range. So if I catch a perch in the Patapsco, that fish was matured in the mouth of the river, and it spawned at the headwater. So it went upstream, it goes downstream, it doesn't really leave that river. Whereas if I catch a striped bass out here, it could have spent most of its life in the Boston Harbor instead of the Baltimore Harbor because of the migration of that fish. So white perch are one of the reasons why we use this for comparison. People eat them. They have a very small home range. And just for understanding this diagram, or this chart, on the left, this is the total PCBs in the tissue. The boxes, the top and the bottom, the top is the 75th percentile. The bottom is the 25th percentile, so saying most of your sample is going to be somewhere in that box. And if you look way down on the bottom, this dashed line, that's the safe limit for recreational anglers. So across the board, we have a bit of a problem. And this is over a 16-year sampling period. And this confirms some results that have been put out that said really the levels in white perch is strongly associated with the land use of that watershed. And what it comes down to is the more impervious surface you have, the higher the PCB levels in the white perch. So what we tend to see is a trend where the eastern shore has lower levels than the western shore. This correlates to historical use and land use as well. Another species we like to compare with, just to kind of see do we see similar trends, are channel catfish. Again, this is a very popular recreational fish to catch. And we see the same trend where urban areas and suburban areas are much higher than our rural areas. And right here in the middle, I like to call this the Washington, D.C. effect. So this is the upper Potomac River, which is upstream of Washington, D.C. This is the Washington, D.C. portion, and then this is downstream of Washington, D.C. So the levels go up as you go through the Washington area, which Washington has had a historical problem with PCBs, like the Anacostia River, where you had a lot of old industry and a lot of accidental releases. So let's take a little bit of a closer look. So this is where we're at right now. This is Baltimore Harbor. We are approximately here. And I was asked by the city and the county to kind of give a brief look at, so what areas should we really be concerned with? So we said, hey, let's look at some of the white perch values and see, do we see any trends? Are there any hot spots we should look at? So these are just some different spots we've sampled over this 16-year period. And what we find is that for the most part, the top dashed line, this is the average level for the Baltimore Harbor. And the bottom, this is our risk threshold 39 micrograms per kilogram. This is the risk threshold for recreational anglers. We find that unless you're eating fish out of the Gunpowder River, all of them are above that risk threshold for lifetime cancer risk. And really, for the most part, there is no hot spot, except for Curtis Bay. And for those that may not be familiar with Curtis Bay, there's multiple Superfund sites at Curtis Bay. Most of the release is associated with the Coast Guard maintenance facility there and the Army shipping depot. But there's a host of other contributors in that area. And when we're trying to think about, okay, we said PCBs were banned in 1979. We're coming up on 40 years since their phase out. I say banned. New manufacturing stopped in 1949, but a gradual phase out of PCB use occurred, continued to occur. And what we'd expect is that things should get better. And in fact, Maryland Department of the Environment assumes a 4% decrease per year of PCBs based on natural recovery. But if we look at the fish levels, on the top, this is the eastern shore. On the eastern shore, we see this statistical decrease over this 16-year period. So those levels are in fact going down, and most recent sampling, those levels were below the safe limits for recreational angling, which is also good because the eastern shore is where there's a commercial fishery for white perch. So this goes out to a global market. But on the western shore, our side, sorry, our levels more or less are at what we consider a steady state. So they're not going down statistically over the 16-year period. And what does this mean for cancer risk? Well, we applied some basic consumption models to say, if you eat fish at this frequency, what is your lifetime risk of cancer? And that makes a really small number, but to make it more digestible, we applied this to out of a population of 1 in 100,000. So that's 1 in 100,000 is what the EPA uses to judge risk based on a certain activity. So out of a population of 100,000, in only one criteria where if you were eating 1 meal per month of fish, over the 15-year period from the eastern shore, would you not be over that risk threshold of 1 in 100,000? But if, say, you were on the western shore, our side here, and you were eating 2 meals per week, which is what the FDA recommends for your human health, to eat 2 meals per week of fish, you would have a 40 in 100,000 chance of cancer if you ate fish throughout your adult life from the western shore. If you looked at the complete lifetime, this includes childhood, so excluding babies, but from solid phase on, from the western shore, you would have a 200 in 100,000 chance of developing cancer over your lifetime from consuming fish from the western shore. So it does have direct impacts to human health. So there is an actual real implication and a known cancer risk associated with it. So this is the question I always get if we're talking about Maryland. What about crabs, right? The good news is crabs are actually remarkably low. And a lot of people will say, how is that possible, right? And I would actually tell you, you can eat 1 meal of crabs per day for your lifetime and only have an 8 in 100,000 chance of death from cancer. So that's a pretty good deal. If you can eat crabs every day for your lifetime, I think you're doing all right. And the reality behind this, as we said, PCBs love lipid. They like to accumulate in lipid tissue, and crab is actually a very lean meat. Also, they don't live very long, so a keeper is only a year or 2 years old, versus a white perch that's 9 inches long has been in that river for 9 years. They grow about 1 inch per year. So they have a much longer time to accumulate things versus a crab, which is actually very young and very low in the food chain. So why are PCB levels still high, right? Who's causing it? Where's the polluter? Who can we go after? That's what everybody wants to know. Well, first we need to say, well, where are PCBs coming from? And to understand that, we need to look at bioaccumulation. So what happens is most PCBs will end up in the sediment. So let's say we have a concentration, this is for DDX or DDT, DDD, excuse me, which is a derivative in DDX from DDT. Get my letters mixed up. If we had 1 part per million in the sediment, we would estimate in the water, we would have about 10 to the minus 4th parts per million. So a lot less in the water and in the pore water than in our sediment. But that will get a little bit higher as we go into our plankton, which gets picked up by our smaller fish, which is at about a half a part per million. And eventually we get to our large fish, which is at 1.7. So as you go up the food chain, you get higher and higher concentrations. That's why things like killer whales have such high levels compared to krill. So it goes up as you go up. And fortunately for humans, we really like to eat large fish. That's our preferred, generally large predatory fish, which tend to have higher levels. So if we talk about recovery, this would be an example of natural attenuation. What natural attenuation is we've got our old historical sediment. It's contaminated on the bottom. We've got worms living in the sediment. The fish are eating the worms. And it's all at a big equilibrium. But we have new sediments that come in. And as the new sediments come in, it's forming a natural barrier to the old sediments that are underneath. And if these concentrations are lower than the old deposits, you have less accumulation in the food chain. But if we have ongoing sources, you still have that new sedimentation that's occurring, but we have ongoing new inputs into the system, at which point we see what more or less is like a steady state. An example of this would be, say, the Jones Falls. When we have a big rainstorm, it's hard to believe that the sediment coming off the Jones Falls is at a concentration lower than the Baltimore Harbor. It may, in fact, be at a concentration higher than the Baltimore Harbor. We don't really know, because a lot of this work hasn't been done yet. So as we said before, what are the sources? When we talk about this, everyone thinks here. They think big polluter, someone must have dumped it, where's the source, let's go find it, make them pay for it. When reality is, window caulk for some places was 50% PCBs. For window caulk that was in place before 1980. We also had electrical transformers, and then this picture is actually courtesy of my mom, who's in the audience right now. I love this picture. Their next door neighbor had PCBs in their front yard. This is a neighborhood in Annapolis, in a very suburban area. This is in the cul-de-sac. And I'm like, all right, PCBs in the yard, take a picture. So takes a picture. This is a pumping truck that is pumping a PCB sludge that was found in the front yard when they were installing a gas line. And if you see where this hay bale is, that's an above ground electrical transformer that's currently PCB free. But the neighborhood is older than the ban on PCBs. So my guess is before there used to be an electrical transformer there that leaked, or then they were putting the new one in. Maybe they just put it next to the road to get picked up later. It suddenly was lighter. But where she's taking the picture is on a storm drain that leads directly into the South River. So this is a very different paradigm than the Hudson River, right? This is a much more widespread, diffuse source that's much harder to track down. Which kind of leads into another area that I've done some research in, looking at the Baltimore's wastewater treatment plant. So this is Back River. Many of you know it by the golden eggs. That's their more affectionate term. And what we did is we wanted to say, okay, where are PCBs coming from? Because we started seeing really high levels in the biosolids. Biosolids are what you get left over after you've done all the microbial processes. It's not poop, but it's actually like a breakdown material. And this plant gets about 120 million gallons per day of sewage coming in. All right, its design capacity is 180 million gallons per day. When it gets a big rain, it goes all the way up to 300 million gallons per day. It produces 450 wet tons of biosolids per day that have to be disposed of. And in our area, all of these are land applied as an agricultural fertilizer. And it services 1.3 million people, and it's a mixture of residential and industrial waste. And what's really interesting about ours is that there's no surface water going into the wastewater treatment plant. Our collection system in Baltimore is one of the oldest in the country, and it was built after the 1905 fires in Baltimore. They figured, hey, the city's flattened, great time to do some construction. That's when they put the sewer lines in. And what we found was that this plant receives 178 grams of PCBs per day. To put that number in perspective, that's the equivalent loading of the Susquehanna River to the Chesapeake Bay. So this plant gets the same amount of PCBs as the drainage basin for the entire Susquehanna River that encompasses Maryland, Pennsylvania, New York, and Delaware, I think a small part, a little bit of New Jersey too. So massive amounts of PCBs in perspective. Most of it ends up in biosolids, which gets put on the land. And about 3% or so ends up in the final effluent that goes into the fish. And unfortunately, that 5 grams per day is the maximum amount you can discharge into the back river while keeping fish safe. And what is 5 grams per day? Don't worry, this is just water and a little bit of iodine so you can see it. This is what 5 grams per day of PCBs would look like. For the entire back river is what the loading needs to be to keep fish safe for human consumption. So it's not a lot, but it has a lot of ramifications. And when we looked at the biosolids, we did a comparison just to kind of see, is this ubiquitous everywhere? So we compared suburban to urban. So this is the Little Patuxent. So if you live in Columbia, this is your plant. And if you live in the Baltimore area, we're in Back River. What we find is that the levels are pretty consistent in the biosolids across 16 months. So what that told us was that whatever's being released, this wasn't a one-time occurrence. This is pretty much, again, we're saying is a steady release of PCBs in the system coming through. And when we start saying, what are the sources? I love this slide as well, talking about, you may have heard about the Fatberg in Baltimore. So they assume this is about a 40-year deposit of fats, oils, and grease, affectionately called fog, that was in the Baltimore sewer line. So we said that PCBs love fat. So there was a period where proper disposal of PCBs was the shop drain in your floor. If you dumped PCB oil down the shop drain in any one of the facilities in Baltimore that may have been working with them, it would have strongly adhered to any of these fats. So most of the sewer lines in Baltimore look like a clogged artery. There's inches of fat clogging and lining the whole sewer line. It will take decades to deplete this reservoir of PCBs. So we actually have a new project coming up where we're partnering with Baltimore City and Baltimore County to start looking at this problem to see, is this an ongoing source of PCBs and can it be cleaned out and removed? It's a lot easier to find the source than it is to upgrade the treatment plant. So with that, I'm going to turn it over to Kevin, who's going to talk a little bit about the good news. So now that I've kind of ruined your breakfast and everything else.
Are we saving questions to the end?
Yeah, we'll save them to the end. So I think Trevor's convinced you that there actually is a problem with PCBs. I mean, the thought was PCBs, we stopped manufacturing them in the late 70s, so it shouldn't be a problem anymore. And I think he's described to you why it's still a significant problem. So I'm going to start with a video. I'm going to talk about the different techniques that are used currently to deal with PCB contaminated sediments. Then I'll get into some new things that we're working on as well. And so one of the most common treatments, and this is how the 20 miles of Hudson River was treated, was dredging, which they use a dredge. They essentially just dig up the sediments. And you'll notice as they dig them up, a lot of sediments are being released. And a lot of those sediments could have PCBs in them, and they're being washed downstream. They're then loaded into barges. This is exactly how the Hudson River was done. Then those barges go away and go to a dewatering plant. And I'm not going to continue the video, but in the dewatering plant, let's see. In the dewatering plant, they dewater the sediments. The water is then cleaned and then it's returned to the river. And then the solids themselves are usually sent to a landfill. So in the case of the Hudson River, they built a huge dewatering plant. They built a dedicated train line, and they shipped the dried sediments out to Texas and buried them. So we didn't eliminate the PCBs, we just moved them somewhere else. And frankly, putting them in a lined pit inland is a lot safer because in the aquatic environment, those PCBs, as you saw, get into the food chain. If they're in a line pit in the land, at least they're not going to get into the food chain at that point, unless, of course, there's some disaster. A second common process is capping. And this picture up here shows you a barge with a spreader. It's just like a salt spreader on the back of a truck. And essentially it's taking gravel and it's spreading it along, and they're just going along and covering up the sediment that's contaminated with PCBs. And you can see this profile here. Here's the contaminated sediment, and you can see all this gravel on top. So essentially you're covering it up so that the animals that would normally interact with the PCBs and work up through the food chain are no longer interacting with the sediment. And eventually this will be covered up with fresh sediment, and you'd have a new ecosystem. The problem with both dredging and this is it's very destructive to the environment. You're never going to use this in a wetlands area where you want to preserve the ecology because you just destroy it. It's more common in the center of rivers where you're not concerned with the benthic activity or the organisms that are down in the mud, and you can just move them or just cover them up. But it's a destructive process. And particularly dredging is a very expensive process. I mean, that can be $1 million an acre just to do dredging. Capping is about a fifth to a third of that cost, but it's still expensive. A new technology, and this has been developed in Upal Ghosh's lab where Trevor works. He's been doing a lot of work with activated carbon. Activated carbon, it turns out, is very good at absorbing PCBs. So if you put activated carbon in the environment, the PCBs will be absorbed to the carbon, and they bind tenaciously. And what happens is you put the carbon down, and then you have all these worms and all this benthic activity going on that mix this carbon down into the sediment. So you can use this natural process, or you can put the carbon into the sediment and use a giant tiller and just mix it in. And what happens is when you add carbon, this is an experiment showing here, this is the regular sediment with PCBs and the worms in it. And what they did is they harvested the worms and they extracted the worms and looked for PCBs. Those worms would work their way up the food chain. Larger animals would eat them, fish would eat those animals, and they work their way up. So if the worms have PCBs, they're going to get into the food chain. And what happened when you had carbon in there, you see this tremendous reduction in the level of PCBs in those worms. So it was very effective. Even though the worms would actually ingest this sediment, the PCBs were not getting into the gut of that worm. So you were essentially blocking the PCBs. And you could apply this. This technology has been tested. It's starting to be used. And it's been actually approved as an alternative method by the EPA. And there are different ways to apply it. You can essentially put it down in the form of a mat of carbon. Can just add it from a barge, just like a cap. Or you can even do a rototiller, like I showed you in that previous picture, and actually mix it into the sediments. There are a number of ways to actually apply it. Now, this is a great method. It's currently being used. The one limitation is the PCBs are still there. Now, they're adsorbed to the carbon, and over time they're going to desorb, but it's at such a low rate that the concentrations getting into the water column are still going to be low. But you still have the PCBs. Whatever PCBs were there originally are still there. So what we've been doing is we've been looking in a way to go to the next step. Not only absorb the PCBs using carbon, but then actually degrade them. And we're using a process called bioremediation. Essentially, this is the dictionary term for bioremediation, treatment of pollutants or waste, spill, contaminated groundwater, or industrial process by use of microorganisms that break down the substances. So we're actually want to use microbes to break down the PCBs. And this is where my research began 20 years ago, was to identify microbes that could do this so that we could go back to the environment someday and actually apply them. So the advantages of using bioremediation. First off, we know we have PCBs all over the world, and just because of atmospheric deposition, PCBs getting into the atmosphere, we've got PCBs in Antarctic, we've got PCBs in the Arctic. So even where there haven't been industrial processes globally, it's a problem. So We need technologies to deal with them. The current technologies, as I mentioned, capping and dredging, they're destructive. So there are a lot of environments where you're going to use those. They are advantageous, but there are other environments where it's either too expensive or you don't want to disrupt the environment, particularly with very wetlands and areas that are environmentally sensitive, where you don't want to disrupt the ecology. On the other hand, using bioremediation has several advantages. It's actually less expensive. It's more cost effective. It's more equivalent to the cost of capping, with the advantage you're actually getting rid of the PCBs, like dredging. You actually degrade the PCBs. It's very easy to deploy, as I'll show you in a moment, and it's minimally invasive. One of the projects I'll be talking about is actually on the Quantico military base. It's an active training area. And to bring in large equipment to work in this area, just because the grounds are needed for active training, it just can't be done. This type of technology, we can go in, very little in the way of large equipment, and we can get out again. The health risks that are associated with disrupting the sediment. So you can drop capping material close to the sediment, you're probably okay. Dredging, though, you're disrupting those sediments and you're sending contaminated sediments downstream. So you're actually, for a period of time, increasing the risk before you decrease the risk as a result. There's no requirement for any kind of waste management afterwards. Capping, if you want to restore the ecology, you have to bring in a new sediment to restore it. Dredging, of course, you're going to completely disrupt things. And with this case, because you're not disrupting the environment, you don't have to do anything afterwards. You go in, you apply it, you walk away. And in addition to PCBs, this type of technology, if it works and is successful, it can be adapted to other contaminants. We can find different types of bacteria that'll break down different contaminants and use the same approach. So here's how it works. We have two types of organisms. We have an anaerobe, and these organisms essentially breathe PCBs. So they don't use oxygen. They use PCB just like we use oxygen. And they dump their electrons just like we do. On oxygen, they do it with PCBs. So they breathe these things. And what they do is they break down, this is from a gas chromatograph, and this is showing PCBs with 1 chlorine, 2, 3, 4, 5, 6, 7, 8, 9 chlorines up to the end. Now these anaerobes will attack these PCBs with a large number of chlorines, 5 to 9 chlorines. The aerobes won't touch that. The aerobes, on the other hand, once these chlorines are removed, the aerobes can then attack them. What they'll do is they'll actually split the ring then, and eventually, after a series of reactions, you end up with water and CO2. So to develop this, we had to first identify the bacteria. We have an anaerobe, and we have an aerobe. And in this case, this organism was isolated from Charleston Harbor. And this was up in New York State in a landfill. We didn't isolate this one. This was someone else did that one. This is the aerobe. And then what we did is we took those cells, we put them in glass tanks with Baltimore Harbor sediments that were contaminated with PCBs. We just grabbed them from out back here. And what happened was we saw that if we added the microorganisms, we saw a decrease by 80% the amount of PCB. Now this is only after 90 days. We had 75%. Within a year, half a year, we had 80% degradation of the PCBs. Normally that would take decades, even a century, to get rid of the PCBs like that. And if it wasn't treated, there was no real change. So we could show the organisms actually worked. Next, we had to scale them up. And this is our scale-up facility here at IMET. And what we needed to do is get a large number of organisms in order to put them back into the environment if this was going to work. So we learned how to scale these up to very large numbers. And we had to do it in a way that there are no PCBs. We can't grow them on PCBs because there'll be PCBs present, and we can't put that back into the environment. The EPA won't be happy about that. So we had to find ways to grow these without a compound that was considered a contaminant. And, or we had to be able to remove it. And that's what we've done. We've found a compound that we can actually remove just by passing nitrogen gas through it. And so we have no residual PCBs. We scale them up, we concentrate them with a centrifuge, and we put them in a small 20-liter container, and that's what we take to the site. And then finally, we needed a way to get the microorganisms into the sediments. If we dumped them on the surface of the water, they're not going to get down to the sediment. And this is where activated carbon comes back into play. And a product that was developed by Upal Ghosh, lab that we mentioned before that Trevor works in, he actually developed a product that was activated carbon in the form of a pellet that was heavier than water. And what we found is that we could apply the bacteria to this pellet, put the pellet into the water column, the pellets would just go down through the column and into the sediment, and then they break apart. And our bacteria piggyback on the back of these. And so we finally had a way of doing this. We had an effective carrier for getting it there. And these are just small pellets of carbon and other compounds, clay and sand, that are inert. No harm to the environment. They're common compounds found in the environment, so we're not adding anything artificial or harmful. So we take the pellets, we spray the microorganisms in, and the beauty of this product is that you can add it a number of ways. This is an air horn, in which we use high pressure air to blow the pellets out and blow the pellets into the water so they go down to the sediment. This is a telebelt. It's just a conveyor belt we can use to actually apply the pellets. And these were projects where the sediment was actually applied. And the way it works is you add the pellets with the bacteria onto the sediment. You form a thin layer over the contaminated PCB contaminated sediment. Over time, as the PCBs diffuse through that layer, they absorb to the carbon and they're broken down by the bacteria. And eventually you end up with this nice clean layer that covers any remaining contaminated sediment. So you then prevent the PCBs from getting up into the food chain. So I'll talk about 3 projects in which we tested this in the field. The first one is Abrams Creek, and this is on the Quantico Marine Corps base. And what we did is, this is an active training area. We set up several plots. The whole area here is about 8 acres, and we had about 1/10 acre plots that we set up. One plot was a control, untreated. The next plot was just the activated carbon, and the other 2 plots had the activated carbon with the bacteria added. And this, again, there's a hazard sign saying you cannot fish there because of the high levels of PCBs. There's also DDT in this environment. So what we did is we took the sediments back to the lab to just see if this was going to work with these particular sediments. And we took those sediments, we put them in glass tanks. This was a recirculation system. What we wanted to do is we wanted to simulate the oxygen level in the top layer, the temperature, and we wanted to constantly have the water flow like it would in the environment. So we wanted to simulate the environment as much as possible to see if this would work. And what we found, I'm not going to go into all of these, we had controls without the bacteria. We looked at different amounts of bacteria. We added carbon sources. We tried different types of bacteria. And what we found is in the best treatment, this number 6, we had 10 to the 5th organisms per gram of sediment. And we had 78% reduction in PCB levels. And this was after a period of 360 days. So we found that that was the best treatment regimen. That combination of sedimite, cellulose, and 10 to the 5th organism per gram of sediment was the best treatment. So then we went back to the actual site. We grew up the organisms in the lab to very high numbers, calculated how, for 10th acre plots, how many organisms we would need, how much sedimite we would need, and we went back and applied that. So we had 6,000 pounds of sedimite transported to the site. We had a staging area. We mixed the microorganisms. We applied them to the pellets, and then set them in these buckets, loaded up a boat, and then from there, we applied the pellets. And this is the air horn I mentioned earlier. There's a hopper here, and the pellets are actually being applied in one of the plots. So that's how we're getting the bacteria in there. And what we found after a period of 409 days, in the 2 untreated plots, this is the sedimite alone, this is without bacteria, this is sedimite without bacteria. there was no real change. But the two plots where we added the bacteria, we saw a 30% reduction in 409 days and a 52% reduction in 409 days in those two plots. So it worked in the field. This is the first time we actually tested it in the field. This is 409 days. Normally we can let this go for a couple of years. And so this is very early. And what we fully anticipate, we haven't gone back yet, is that this has continued to decrease over time. The other thing we did was we looked at the amount of PCB actually in the water. So this is the small amount of PCB that gets dissolved in water. This is what the the organisms actually see. This is the bioavailable portion. So the more PCB you actually have in the water phase, the more you're going to see in the food chain. And what we found is that untreated is shown here. Sedimite, we see a 62% reduction, but you expect that because we know activated carbon is going to absorb some of those PCBs and keep them out of the water. But with the bacteria, we saw an 84% reduction and a 95% reduction with the bacteria. So it was very effective at keeping the levels of PCBs very low and keeping them out of the food chain. A second site was a wastewater treatment pond in Alta Vista, Virginia. And this was an old overflow pond. They now have a modern treatment plant here in this small town. But this used to be the treatment. It was just an open water pond. And early on, there used to be Burlington Glass Fabric Factory was right nearby. It was located right up here. And at that time, PCBs weren't considered a hazard. So they would just dump their PCBs right into the sewer. And it would end up in this pond. As a result, the levels, I mean, normally in Baltimore Harbor, we see levels of 2 to 8 parts per million. Here, they were getting 17,000 parts per million. It was an incredibly high amount of PCB. So the town contacted me and said, what can we do with this? They looked into dredging, but the cost for the town to dredge that and take it somewhere else it was going to be like $3–4 million, which the town couldn't afford. Plus, they found out that even when they moved it, I think it was going to go up to Michigan, they retained the liability. So anything happened to that decades to come, they were liable for that. So we decided to try what we were doing there. And what we did is we put in some small, these are barrels, these caissons. We just took oil barrels, took the top and the bottom out, and we put them in. And we did different treatments in these barrels to see what would happen. And what we found is that without treatment, there's not much change. You see this bounce around because PCBs, because they are kind of oily, they tend to clump. So you tend to see the levels aren't, depending on where you sample, they can vary quite a bit. But in the treated, you'll see it dropped right off. Now this is after 2.5 years of monitoring. The goal was to get to 50 parts per million, which was the accepted level by the EPA and by Virginia. And we achieved that. After this time, we got down to just below 49 parts per million. So this suggested that in treating the whole pond, which was several acres, this technology could work. And we've got a project there now. We're using larger caissons. These are 10 feet across. And we're trying some different treatments. We got a control. We've got nutrients with the carbon, carbon in the bioamendment, and just nutrients alone to see what would happen. And this is an ongoing project. But when we just mixed it, we actually saw degradation of PCBs that we just mixed. And we think that's because we introduced oxygen, and there are a lot of microorganisms already in there that will attack PCBs. If we just added nutrients, same effect. Both of them leveled off. But where we bioamended, you can see they dropped off as high as 57%. And it isn't leveling. It's still going down. So we're continuing to monitor this to see how low we can go. And we're hoping to achieve that 80%. Because if we can achieve 80%, then we'll have solved their problem for treating the whole pond. And a last case study, this was done in a Curie Atoll in Hawaii. This atoll is located beyond Midway. It's the farthest point of land on the Hawaiian Islands. It's very remote. The only way to get to it is by boat. And this is an old Loran station that's been decommissioned. And what they had done is there was an electronics dump here. They would take all the electronics when they didn't need them anymore, and they'd dump them. A lot of them had PCBs. And what they wanted to do, this is now a preserve, they wanted to move these away from the water so they wouldn't risk contamination and into the highest point of the island, which was probably about 2 feet. It's just an atoll. But the idea was to get it away from the water. It's too remote to move them. They needed to do it there. And so what we did is we suggested, well, let's try using the microorganisms to break them down at the site as you're doing your landfill. And so what they did, the other caveat to this was Hawaii, you can't ship organisms from the mainland to Hawaii without a lot of paperwork. So we had to use Hawaiian microorganisms. So we had to have them ship soil to us. We enriched these organisms, and then we shipped them back, and that's in this container here. We grew them up and shipped them back. The USDA met the plane and confiscated the organisms and made sure that they got onto the right plane that was going out to this island. So it never left their site. So our Hawaiian organisms went back to Hawaii, and they were mixed with a buffer, diluted, and then as they were moving the contaminated soil into this pit, they would then, this is a sprayer on here, a chemical sprayer, and they're just spraying the microorganisms over the soil as it's being put into the pit. And this is still ongoing, and because it's so remote, we can't go back there to sample periodically, so we actually have the samples upstairs. They were shipped back. We have them in environmental conditions that are similar to this, and we're monitoring them up in the lab now. And so far, we've seen a 36% degradation of the PCBs in the soil. So we're actually out there. We're applying this to the field. And it looks like it's a method that could work. We're very hopeful. And just comparing everything that's out there, dredging, it does reduce the levels of PCBs, but there's an increased health risk because you're disturbing the sediments in the process. So there's environmental disruption as a result. If it's a pristine area you want to preserve, you're not going to use dredging. It's very expensive. You got a lot of heavy machinery, has a very large carbon footprint. You have to do something with that afterwards. So you're dealing with long-term storage. If you have to restore the habitat, there's costs suited with that, and you're not going to use it in a wetland. Capping, it doesn't reduce the PCBs at the site, but the health risks are lower because you're not disrupting the sediment. There's environmental disruption. It's a little less expensive to do, and it can have a limited life. So that cap, in many circumstances, can be somehow broken. It could be ice formation. It could be currents. A number of events could occur that could actually disrupt that cap. So you have to monitor it and maintain it over time, which is additional expense. Activated carbon, on the other hand, it doesn't reduce the level of PCBs, but the health risks are low, environmental disruption is low, energy cost is low. There's no waste management afterwards. There's no restoration cost, and it's very well suited for environmentally sensitive areas. In bioamended carbon, same thing, except this added advantage. You can actually reduce the PCB levels at the site. So that's the added advantage of using this approach. So finally, we know PCBs aren't manufactured anymore, but they remain in the environment. They were a miracle chemical. They were stable in industry, and now they're stable in the environment, so we still have them. The risk levels in the Chesapeake Bay, fish continue to exceed the EPA risk threshold. So even though we're not manufacturing these compounds anymore, they're still a problem. The conventional methods exist, dredging and capping of PCBs, but we also have methods now for in situ environmentally sustainable methods. One's the carbon, activated carbon alone. The other's bioamended activated carbon. And finally, if we're going to treat the harbor out here, we can't just go and treat the harbor. So if we were to spend millions of dollars cleaning that up, and we still had PCBs coming in, as Trevor talked about, from Fatbergs, sewer lines, from other sources that we're not even aware of, then that money's wasted. First, we have to identify the sources. And once we identify the sources, then we can use these various methods to actually clean up the environment. And with that, the end of my talk.
Thanks to Trevor and Kevin, and we can take a few questions, starting with Al and then going to Gerardo. Al.
It relates to two things. So are you guys thinking of using this? Where I'm going with it is actually the lowest level of PCBs were actually in your back river fish. If you look at your data. And what's interesting is, are you thinking of using this in the biosolids? Your method in the biosolids?
My method wouldn't, well, it wouldn't work in the plant itself because of the long incubation time. And the retention time in the plant is very small.
Well, I'm talking about the biosolids before they get put on. They'd be put aside for a period of time, incubated with your guys under valid conditions before you put it back on the land.
It's possible. It would depend on the expense. You know, there's a lot of biosolids.
There's a lot of biosolids. Slowing that process down, because it's 450 tons per day. So they need to get it out quickly, and there's a big disconnect right now because even though the levels are high in Back River, the allowable levels for land application is 50 milligrams per kilogram, which is about 3 orders of magnitude higher than what you can have in sediments. But it's mostly because we don't eat earthworms or robins. And they're the ones that are most at risk. So the regulation is really driven off of human health risk. So the aquatic food chain is much more sensitive than the terrestrial food chain. So right now, we did look at adding activated carbon to biosolids, and that actually will sequester the PCBs in the biosolids, and it won't go into the terrestrial food chain. So we have looked at that portion.
Okay, let's move to Gerardo.
Yeah, I have looked at the bacterial composition of the carrier, let's say, after the treatment period. I mean, are the strains basically that the grain PCBs that you have incorporated into the system remain there for a year? Do they proliferate? Are they replaced by other?
No, both those organisms are ubiquitous. They're everywhere. I go out to the harbor, Charleston Harbor, I could go out to any aquatic site, and I'm going to find them. The problem is PCBs, they don't make a great living on PCB. Well, they make a great living. They survive, you know, so that's a good living for them. But because of the PCBs are hydrophobic, they don't mix with water well, they're not very bioavailable, the numbers in the environment are about 10 to the 1, maybe 10 to the 2 cells per gram. And so you do have natural attenuation occurring. So if we're willing to wait decades or a century, they will degrade the PCBs, but their numbers are so low, we don't see it. It's going to take too long. All we're doing is taking that natural process, and by increasing the numbers 5 orders of magnitude, we're just speeding up the process. So they don't survive well because once the PCBs are depleted, their numbers drop off because they no longer have a substrate to work on.
And we have a question here from Finn.
First thing is more like a commons. When you say Texas, take the waste. So from Hudson River, that's good. They actually took the waste. For the Back River, 100 years ago, when they were built, when it was built, they tried to ask other states to take the solids. You know, nobody wanted to take it. The train went out to countries and came back. That's why they built the 2 golden eggs there, right?
They had a colorful name. They called it the poo-poo choo-choo.
Yeah, it's amazing. So I have more like a technical question, whether there's a way to increase efficiencies by increasing the surface area for your bacteria to attach. Right now, you just sprayed it on the sediment, right? Mm-hmm. So it's something that you can do, like what we did in the art. You know, increase the like microbeads. You know, soak it in the bacteria in a little bit more modified structures, so they have more surface. Mm-hmm. Maybe that will increase the efficiencies.
The anaerobic process is slow. I mean, even if you have direct contact, it's still a slow process, so it's always going to be rate limiting. The carbon itself has a lot of surface area, it's very porous. So when we spray those organisms on there, we are creating a large surface area for those organisms. So in a sense, we're doing that with the carbon itself.
Yeah, I was thinking about activated carbon. There's a lot of pore inside, right? So maybe you can make good use of those areas.
Well, we are, because when we spray it, they're being absorbed into those channels. And the other advantage of the carbon is it's attracting the PCBs. So the PCBs are coming to the microorganisms. That's the idea, is that as PCBs desorb from any other solids that are in there and move towards the carbon, they have to pass by the bacteria. And that's what makes that process relatively efficient. So in a sense, we are doing what you're suggesting.
Yeah, it'll be interesting to see some microscope image, SEM image.
We have one.
We do have that. We had a CERTA project. We were doing that, yeah.
Good. Other questions?
Kevin, how's the anaerobe surviving? I mean, you're opening up, the very act of spraying this stuff. I mean,
Al, Ryder, and then John.
Okay, so, all right. Remember, there are a lot of micro niches and a lot of pores. And, we think of things being aerobic or anaerobic, when in fact, we have biofilm formation on there, we have a gradient. And the anaerobe itself actually is somewhat tolerant of oxygen. It won't necessarily function, but it'll tolerate it. But then you get them on these particles, they're exposed to air momentarily. But once they're in the particles, you're going to have this gradient form. And that's how we believe, we don't know, we don't have the data for it, that both the aerobe and the anaerobe are surviving together on these particles. And we know both are active.
Great. Ryder.
Yeah, so Trevor, when you look at your fish, when you sample the fish, are you looking at a pool of different tissues or only fishes that have high levels of fat?
So these tissues were collected for human health risk. So they're prepared in a way that people would consume. So white perch are fillets with the skin on and descaled, because that's the way a white perch is typically consumed, versus a channel catfish is filleted and deskinned. So it is not a whole fish assay, but each sample point represents a composite of 5 fish that are homogenized and then run. So,
I'll follow up if I may. When both fish and crabs were produced, the eggs are very, very rich in lipids. So is it possible that the eggs and embryos accumulate a lot of PCBs and affects actually the reproduction of the
So PCBs are an endocrine disruptor, and there could be acute toxicity there. We find with PCBs, the organisms in the environment tend not to have as much of a toxicological effect from it, just because it's more of the long-term body burden that we're looking at for risk. So PCBs tend to be an issue if you live for a long time and you are high in the food chain. That's very bad news for like us or orcas or things like that. But for fish, they tend to still maintain relatively low percentages compared to their overall body burden, if that's kind of a...
Good. John, and then Sook.
So I was curious, how did they know that they had, the workers that were digging in your mom's front yard, how did they know that they had stumbled across PCB sludge?
I asked that. I think they just hit an oiled sludge, and they sent it in for analysis to find out what it was.
I was just going to say.
Yeah, I got the lab printouts, and it's a very convenient lab analysis that's done, which just says that it's safe for disposal wherever you want to put it. Because it's below 50 milligrams per kilogram. So at 50 milligrams per kilogram, it then becomes a REC C waste. It has to be disposed of in a hazardous waste landfill. Our nearest one is Illinois. So the cost goes up really high. So it said, nope, not a PCB waste. If it was our lab here, we would label that as PCB waste, and it would go through the process. But according to the reports, it's all under 50 milligrams per kilogram, therefore it's not a PCB waste.
So these guys they actually tested it as opposed to just...
No, they tested it, and then it got pumped out. It got pumped out and went to a landfill. That leachate then went back into the Back River wastewater treatment plant. So it's just kind of, we just kind of put it in different boxes.
I think they filled the hole with concrete afterwards. They came in. Yeah. So it was kind of strange because what was happening is they were trying to run a gas line under the street to this lady who wanted her emergency generator run off gas, not electricity. So as they went under the street and they're digging the hole, they went, whoa, what's this? But then eventually they just came and once they pumped it all out, they just poured cement into it.
Let's take one or two more questions. Sook and then Laura. Sook.
My question is, Kevin, I might have missed it. What's the ratio of anaerobic, aerobic bacteria in the mix?
1-to-1. Yeah, we tested both in the 1-to-1 ratio, 10 to the 5th each per gram of sediment.
Laura.
So I noticed when you were looking at the decrease in PCBs in the Hawaiian terrestrial environment, that was the drop that was the least. It was around like 32% over that long period of time. And that's surprising because in the water, you're waiting for the pellets to sink down and find these anaerobic areas, and that's where you're finding higher levels. So why do you think that the terrestrial environment isn't?
That was a unique situation. Now in that case, we only used the aerobe because the PCBs had broken down enough that we could get away with the aerobe, and the other reason was it would take us 2 years to isolate the anaerobe, whereas the aerobe we could do it in 6 months, and we had a limited time frame to do this. So part of it is that it's only the aerobic process, but the other part was what we wanted to do was use activated carbon in the site too, because activated carbon, when you put the organism in activated carbon, the PCBs are absorbed to the carbon, they come to the organisms. The company we were working with didn't want to use the carbon. So I think that slowed the process down. We were essentially just spraying these organisms on what was a sandy soil. So they're very vulnerable to the moisture content. Now, PCBs aren't going to stick to sand like they do in organic materials. So they're going to be very available. But we didn't have great control of the moisture content. We made sure we added a lot of buffer and increased the moisture. But it's going to vary quite a bit. So I think the lack of carbon, I think having carbon in there we would send much more impressive results.
Okay, so we can keep this discussion going and finish off the food at the same time. I want to thank Molly for her help in putting this together. I also ask you all to look out for our next public lecture, and we'll be doing these on a regular basis. And please join me in thanking Trevor and